Hello, students. This is Mr. Allen, and today we're going to look at section 8.2, which is on series and convergence. I am going to go and do this video with the smartboard so that I have a little bit more freedom with the notation. I'm going to try to keep this video between 10 to 15 minutes, and I am keeping track. So what we want to be able to do here is understand the definition of a convergence infinite series. We want to use the properties of infinite geometric series and use something called the Nth-Term test to determine if an infinite series is convergent or divergent, or I guess divergent specifically. One important application of infinite series is that it represents an infinite summation. So in section 8.1, we looked at what we call sequences. And so a series is the summation of terms in a sequence. And if we're talking about an infinite series, then we're talking about a sum of infinitely many things, which in some ways seems like that can't be done, but we're going to actually find out that it can. In fact, you'll many times just hear me refer to it as a series instead of an infinite series. The numbers A1, A2, and A3 are the terms of the series. For some series, it is convenient to begin the index with 0, and then others we will begin it with 1. As a typesetting convention, it's common to represent an infinite series as simply the summation of A sub n. So in such a case, we start the value of the index must be taken in terms of the context of the statement. So if we are going to have A sub 1, then the sum of the first 1 terms is just going to be A sub n. The sum of the, by the way, these are what we refer to as partial sums. So partial sum, so if I want to know, we're talking about the sum of the entire series. So if I want to know just the first term sum, that would be S sub 1. But S sub 2 is the first 2 terms added together, and then on down the line, S sub n is the first n terms. If the sequence of partial sums converges, then the series is said to converge and has a sum indicated by the next definition. So here's the definition of a convergent and divergent series. For the infinite series, summation of A sub n, the nth partial sum is given by the following definition. If this sequence of partial sums converges to S, then the series summation of A sub n converges. If the limit S, the limit S is called the sum of the series. So S is equal to A sub 1 plus A sub 2, blah, 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 all the way to A sub n plus blah, blah, forever. If S sub n, if this sum diverges, then we say this series diverges. So let's go ahead and look at our first example here. In our first example, we have the summation of 1 over 2 to the n. And I'm just going to list out a few of these. So this is equivalent to 1 over 2 to the first, plus 1 over 2 to the second, plus 1 over 2 to the 3, plus ... plus 1 over 2 to the n, plus ... So that's what this sum is. And by the way, notice we're going to infinity here. So the question says, what's the first 3 partial sums? Well, S sub 1, which is A sub 1, is simply 1 over 2. So there's our first one. S sub 2, which is A sub 1 plus A sub 2, is going to be 1/2 plus 1/4, which is 3/4. And then S sub 3, the third partial sum, is going to be A sub 1 plus A sub 2 plus A sub 3, which is going to be 1/2 plus 1/4 plus 1/8, which turns out to be 7/8. Then it says use the closed formula for the sum to find the nth term. So here's the closed formula for the sum, and I claim that you can actually see that very easily from these partial sums. So now we're going to try to see if this series converges or diverges. So what we're going to do is I'm just going to take the limit of this sum. So I'm going to do the limit as n goes to infinity of S sub n. So that's going to be the limit as n goes to infinity of 2 to the n minus 1 over 2 to the n. And we can play the same trick that we've played many times, which is going to be the limit as n goes to infinity of 1 over 2 to the n minus 1 over 2 to the n, oops, and this is 2 to the n, divided by 2 to the n over 2 to the n, which is equivalent to the limit as n goes to infinity of 1 minus 1 over 2 to the n over 1. So that's going to give us 1. So now if we go back to our theorem here, the limit s is called the sum of the series. Where's the convergent part? Here we go. If the partial sum converges to s, then the series converges. So therefore, in this case, since we get 1, this is going to converge. This series is going to converge to 1. So it's going to grow, but it's going to get no larger than 1. In fact, that's what it converges to. Okay, example 2. This is the nth partial sum again. So we're going to try to find the first 3 terms, and I'm going to just kind of write these down. We could do these the hard way, but it turns out that this one is 1/2. S2 turns out to be 2/3, and S3 turns out to be 3/4, and then on down the line. And if we want to now figure out what the limit as n goes to infinity of s of n, so that's going to be, oops, I need to put my limit symbol in here. We need to do the limit as n goes to infinity of 1 plus 1 over n plus 1. Well, we can clearly see that that's also going to give us 1, and therefore it converges. And just to let you know, this example here, we're going to come back to this one. So let's keep this one in mind. And then finally, let's look at our last series. In this series here, I am going to write this one out. This series is 1 plus 1 plus 1 plus 1 plus all the way to infinity. And it doesn't really take too much of an observation here to realize that this is going to be infinite. So basically, the formula for s sub n is n. So if we do the limit, s sub 1 is 1, s sub 2 is 2, and s sub 3 is 3. And then the limit as n goes to infinity of s sub n is infinity. I'll just say, I'll write d and e. How about that? It's d and e. And that, therefore, this one diverges. Okay, so in our first example here, let's go back to that. Our first example, we saw that it converges, and it converges to 1 here, this sum. The second one also converges to 1. Very different looking formula there. And then this third one was an example of one that diverges. So remember in that second example, this is example 2, I said I wanted to come back to that, which is this guy here. And just to make sure you're clear, this is the same thing as this. So this is a sub 1, this is a sub 2, this is a sub 3. Now here's the interesting thing about this, and this is why I'm coming back to this. Notice that this minus a half and that plus a half would cancel. Notice that this minus a third and this plus a third would cancel. In fact, once you run down this line, this list of numbers, everything is going to cancel, and the only thing we're going to be left with is 1. And that is exactly why the series converges to 1. This is called a telescoping series, and it's one that you need to be aware of, because if you don't recognize it, it's really difficult to calculate this sum. So note that the second term is canceled by the third term, etc. So this is called a telescoping series. Because the nth partial sum of this series, s sub n, is b sub 1 minus b sub n plus 1, and as b goes to infinity, this is going to go to 0. So it turns out, in this last example, this is the formula to find the sum of a telescoping series. So it's the first term, a sub n, or in this case, b sub 1, minus the limit of the last term. All right, so now we're going to shift gears to geometric series. And here's an example of a geometric series. This was example number 1. This is a geometric series, and here is our general form for a geometric series. So now we're talking about, last slide was telescopic, this one's geometric. So geometric series has a common ratio r, so that's this thing here. In this example here, the common ratio is 1/2. So in this example here, r is 1/2. And we should note that this cannot be 0 in order for it to be geometric. And here's a theorem. This is important. The convergence of a geometric series. A geometric series with ratio r diverges if the absolute value of that common ratio is greater than or equal to 1. If its absolute value is less than or equal to 1, I'm sorry, if it's less than 1, strictly less than 1, then it converges. And if it converges to a over 1 minus r. So let's go ahead and look at a couple of examples of geometric series. And make sure I got my notes in order here. Okay. So this one here can be rewritten as such in going from, oh, and I should note one other thing. I make a note that the geometric series tends to start with the index of 0. So here we've got the index of 0. So this could be rewritten. I'm just rewriting this as 3 to the 1 over, I'm not writing this correctly, guys. Sorry about that. It should be 2 to the n. 2 to the n. Okay, so this is equivalent to this. All I've done is I've pulled out, notice that 3 is not to a power n, and 1 to the n. I mean, we could also think of this even further. Let's just take it one more step. Is 3 times, and I'll write this as 1 over 2 to the n. These are all equivalent forms. So therefore, we know that the r, the common ratio, is 1/2. And by the way, the absolute value of 1/2 is less than 1. So then the absolute value of r is less than 1. So therefore, we can conclude that this converges. We know that this is going to converge. And that's all it asks us to do, is to figure out the convergence. I'm actually going to go ahead and find the sum for you, though, and I'm going to use this formula right here. It doesn't really ask us for that, so let's do that now. Let's do it in purple. So S is going to be equal to A over 1 minus R. So in this case, A is 3 over 1 minus, and then R was 1/2. So it turns out that the sum of these infinitely many things is going to be 6. It's going to be 6. Last one here, this is very easy. This is already a geometric form. So here A is 1, R is 3/2. The absolute value of R here is greater than or equal to 1, so it diverges. So I don't have to go any further. This sum goes to infinity, diverges. Here are some, this is from our last example. So here's some of the first terms. And you can see that if we did an approximation with our calculator, even at n equals 500, we're already pretty much to our sum of 6. And then our second one, with 10 terms, we're at 170. At 100 terms, we're at 1 followed by 18 zeros, basically. I'm not going to write all 18. And then when you get to 500, this thing has already got 88 decimal places that you'd have to move that. So this bad boy is tending towards infinity. This guy here is tending towards 6. Convergent, divergent. So here's a couple of properties. These are familiar from what we've done in the past. Constant multiplier, you can pull out the C. You can add those limits. And then you could subtract in this case here. Now, the last thing here I want to wrap up here, we're getting close to time. I'm actually going to, this one here is important, but this is the main one. This is called the Nth-Term test. And I'm just going to, we're running short on time, so I think I'm just going to jump to it. And here's what it basically says. If the limit as n goes to infinity of a sub n is not equal to 0, then the series has to diverge. Let me say that if I say it, it kind of makes sense. Is n goes to infinity, if that term doesn't equal 0, then it has to diverge. And that kind of makes sense. if I'm not adding smaller and smaller, zero essentially as this sequence goes on, it's going to go to infinity. So that's what this is saying. So let's look at some examples here just to wrap this up today. So example A, 2 to the n. 2 to the n. Well, let's see here. 2 to the n, that's a sub n. So a sub n is 2 to the n. So let's do the limit as n goes to infinity of 2 to the n. Well, that's infinity. Well, if that's infinity, well, okay. Let's go back to this last slide here. It doesn't equal 0, right? So this does not equal 0, so therefore it diverges. Let's look at B. So a sub n here is n factorial over 2 to the n factorial plus 1. Well, let's go ahead and use our formula here. So n goes to infinity, the limit of n factorial over 2n factorial plus 1. And we're going to have to play a little bit of a game. We're going to divide by n factorials again, but I'm just going to cut to the chase, and I'm going to tell you that the answer there is half. Well, 1/2 does not equal 0. Therefore, this one also has to diverge. And again, I'm using this theorem right here. This is a very important theorem. If the limit as n goes to infinity of the nth term does not equal 0, it has to diverge. And then last but not least, let's do this one in red. A sub n is 1 over n. The limit as n goes to infinity of 1 over n is 0. So what can we conclude? Nothing. So this is where we have to be very careful about this nth term test. This nth term test only tells us when a series diverges. Given this, we can conclude it. Then we can conclude it diverges. Here we got it being 0, which means we did not meet our hypothesis. Our hypothesis is that it doesn't equal 0. Hey, this is 0, so we cannot use the conclusion that this diverges. In fact, this is a very important question. Does this converge or does it diverge? Well, we cannot use the nth term test to determine that. And I believe that ends our lesson here today. So.